Good afternoon, everyone, and welcome to episode 3 of Caracal Computing. In this episode, we are going to take a short detour from game development to take a look at something else I've been working on, particle simulations. Some of you may recall the first video I posted to this channel, which was a very crude particle simulation written in C, and a lot of improvements have been made since then. Before jumping into the new stuff, let's take a step back and see how that original simulation actually works. For the sake of simplicity, we will be operating in 2 dimensions so that particles can be approximated by circles. First, we need to know if 2 particles are colliding. To do this, we calculate the amount of overlap. This is done by subtracting the distance between the center points from the sum of the radii. If the overlap is greater than 0, then the particles are colliding. Then we apply Hooke's law so that the particles repel each other elastically. According to Hooke's law, the repellent force is proportional to the displacement, and in this case the displacement of each circle is half of the overlap, assuming the spring constant is the same for each object. And this is then multiplied by that spring constant k to calculate the magnitude of the force. Now we need to calculate the force vector. In this simulation we will ignore torque, so the force vectors between particles are always in line with the displacement between them. We calculate this direction by subtracting the positions of the particles to find the displacement, and then normalizing the displacement vector so it has a length of 1. Multiplying this vector by the magnitude of the force, we get the force vector. Now that the particles can collide with each other, we need to apply some constraints so they don't just fly off the screen. This is done very similarly to how we computed the collisions between particles. Suppose our particle is overlapping with the bottom border of the window. In this case, the overlap is equal to the y position of the particle plus its radius minus the y position of the window border. And once again, Hooke's law is applied to find the resulting force. Essentially, the same process is repeated for the 3 other boundaries. If we don't want this simulation to keep moving forever, then it needs to be damped somehow. And one way to accomplish this is by adding drag. We compute the magnitude of the drag force by squaring the velocity vector and multiplying it by some constant c. Then we normalize the velocity vector and multiply it by the drag force and by -1. This is so that the drag vector points in the opposite direction of the velocity vector. Thus, the drag force will always be slowing down the particle, so to speak. The last force we account for is gravity. For our purposes, gravitational acceleration is constant and always points straight down. So we can simply calculate the y component of gravitational force by applying Newton's second law, and the x component is always 0. We add up all the force vectors acting on an object, and once again apply Newton's second law to find the current acceleration vector. Then, the change in position is calculated by multiplying the current velocity by the time step. This is added to the position vector. The new velocity vector is calculated similarly, multiplying the current acceleration by the time step, and adding this delta to the current velocity vector. By tweaking some of the parameters, it is possible to make this simulation somewhat stable, but it still has some issues. The first issue is performance. Since the simulation is running entirely on CPU, the CPU has to update every object, one after another, for every step in the simulation. This severely limits the number of objects we can simulate in real time. The second issue is stability. Even when it appears to be stable, the simulation sometimes just explodes, and we don't want that. I chose to handle the performance issue first. The easiest way I found to do this was to make the simulation run on the GPU instead of the CPU, since GPUs are very good at handling lots of calculations concurrently. As long as one operation doesn't depend on the results of another operation, both operations can be executed at the same time. Using CUDA, this can be done quite simply. We create an array of particle objects that lives in GPU memory, and create 2 CUDA kernels to perform simulation logic on these objects. The first kernel calculates the acceleration vector for a particle based on its position and velocity, as well as the position of all the other particles in the simulation. The second kernel uses the current velocity and acceleration to calculate the next position and velocity for a particle. When these kernels are called, one thread is created for every particle in the system, so that all the objects are being updated concurrently. The simulation is still CPU bound because of the number of draw calls it has to make, but the performance is much better than it was previously. The second problem to handle was the stability problem. One way to fix this is by using Verlet integration instead of Euler integration. I would go into detail about how Verlet integration works, but honestly, I still don't understand why it works. I just found this algorithm on Wikipedia and I implemented it in CUDA, and I think the results speak for themselves. No weird oscillation behavior, no random explosions, and so forth. And of course, since it's running on the GPU, it is still plenty fast. When I get around to open sourcing this code, I will leave a link to it in the description. Anyways, that's all for today. If you want to see more videos like this one, or if you want to see more game development videos instead, feel free to leave a comment. Until next time, this has been Caracal Computing. Thanks for watching.